Hello students, in this video we will discuss problems based on first definition of derivative. In the questions we will be given one functional equation or functional relation. We will be using first definition of derivative on that functional equation and we will find the function or derivative of function at some point as given in the question. To start with, consider this question. The question is f of x plus y is equal to fx multiplied by f of y for all xy belongs to R. This is called functional equation or functional relation. Now f of 5 is equal to 2 and f dash 0 is equal to 3. We have to find the value of f dash 5. Now we will be solving this question using two methods. In one method we will use direct differentiation of this functional equation, and in second method we will use first definition of derivative in which we will use this functional equation. So let's do this with the first method, direct differentiation. Okay, now here we have two variables x and y. Now tell me, this x and y are dependent variables or independent variables? Actually this relation is in the form of identity. Here we can take any value of x and y. We are free to take any value of x and y because if I put here x is equal to 1 and y is equal to 2, I will put on RHS also x is equal to 1 and y is equal to 2. So we can say here x and y are independent variables. So when I will differentiate this equation with respect to x, I can consider y as constant. However, y is variable, but when I change the value of x, there will be no effect on the value of y. So differentiating now this relation with respect to x, we get f dash x plus y multiplied by derivative of x plus y, which is 1. This is equal to f dash x multiplied by f of y, because f of y is constant with respect to x, so here it will be considered as a coefficient of f dash x. Okay, now depending upon the given data f of 5 and f dash 0, we will put the values of x and y here. Now since we have f dash 0, so I will put x is equal to 0 and f of 5 is equal to 2, so I will put y is equal to 5. So putting x is equal to 0 and y is equal to 5, I get f dash 0 plus 5 is equal to f dash 0 multiplied by f of 5. So I get f dash 5 is equal to, the value of f dash 0 is 3, so I have here 3 multiplied by f of 5 is equal to 2. So here I get 3 multiplied by 2. This means f dash 5 is equal to 6. So this is one method in which we are using direct differentiation. Let's see method number 2. In this we will use first definition of derivative. Now for f dash 5, I can write this is equal to limit h tends to 0 f of 5 plus h minus f of 5 upon h. We know this is a first definition of derivative. This is how we can write f dash 5. Now here we have f of 5 plus h. Now in the given relation we have f of x plus y is equal to fx multiplied by f5. So I can use this functional equation for f of 5 plus h is f of 5 multiplied by f of h minus f of 5 upon h. From this, I can take out f of 5 common outside the limit. Okay, the value of f of 5 is given. Now I have limit of this f of h minus 1 upon h. Clearly this must be f dash 0. The reason is the definition of f dash 0 will be limit h tends to 0 f of 0 plus h minus f of 0 upon h. If I compare this with this definition of f dash 0, that means the value of f of 0 must be 1. So how I can get the value of f of 0, or how I can verify that f of 0 is 1? If you have any requirement, ask the mother equation which will fulfill all your needs. From this, if I want f of 0, I will put y is equal to 0. So I get f of x is equal to f of x multiplied by f of 0. Certainly, from this I get f of 0 is equal to 1. Now one can argue why fx is not equal to 0, because one of the possibilities from this equation is f of x is equal to 0. But if I put f of x is equal to 0, that will be for all x. But here I have f of 5 is equal to 2. So f of x is equal to 0 is ruled out. So f of 0 is equal to 1. That means this is f dash 0. So I have f of 5 multiplied by f dash 0. F of 5 is equal to 2. F dash 0 is equal to 3. So finally I get this is equal to 6. So here we have now two methods. In this we are using direct differentiation, and in this we are using first definition of derivative. Let's practice more. Let's try some more questions. The question is f of xy is equal to fx multiplied by fy for all xy belongs to R. Now f dash 1 is equal to 1, f of 1 not equal to 0, and f of 2 is equal to 3. Find the value of f dash 2. Again, we will be doing this question by two methods. Okay, here we have method 1 using direct differentiation. I will differentiate this relation with respect to x, keeping y as constant. So what will be derivative of this? This will be f dash xy multiplied by derivative of xy, that is y. Okay, this is equal to, now f of y is constant, so on RHS I have f of y multiplied by f dash x. Now depending on the given values, I will select x and y. Okay, now f dash 1 is equal to 1. I have here f dash x, so I will put x is equal to 1, and f of 2 is given 3, so I will put y is equal to 2. So in this I have x is equal to 1 and y is equal to 2. So I get f dash 2 multiplied by 2. This is equal to f of 2 multiplied by f dash 1. Okay, now the value of f of 2 is equal to 3. So let me put here f of 2 is equal to 3 and f dash 1 is equal to 1. So I get f dash 2 is equal to 3 upon 2. We can see this is a very simple method in fact. Okay, now let's do method number 2. In this we will use first definition of derivative for f dash 2. So let's write f dash 2. This is limit h tends to 0 f of 2 plus h minus f of 2 upon h. Okay, next, now I have this functional equation. How can I use this here? One problem is that here we have x multiplied by y and here we have 2 plus h. How can we use this relation here? Okay, we can adjust this 2 plus h as 2 multiplied by 1 plus h upon 2. I am doing this way. The reason is I want here product so that I can use this relation because the relation is for f of x into y. So I am creating here product. Okay, now we can use the given relation. Here say x is equal to 2 and y is equal to 1 plus h by 2. So from this I get f of 2 multiplied by f of 1 plus h by 2 minus f of 2 upon h. Okay. Now f of 2 is common. So here we have f of 2 multiplied by this limit f of 2 is given, which is 3. That means this must be f dash 1. For f dash 1, I have here f of 1 plus h by 2. So in denominator also, I must have h by 2. For that, I will multiply and divide by 2 in denominator. And certainly, this is f of 1. Now f of 1 is not given and we confirm that this must be f of 1. How I can verify this? Why f of 1 is 1? We can get from this relation. In this I will put y is equal to 1. So I get f of x is equal to f of x multiplied by f of 1. I can cancel out f of x because f of x cannot be 0 for all x. So I have f of 1 is equal to 1. So now this is f dash 1. So I have here f of 2 multiplied by f dash 1 upon 2. Put the values of f of 2 and f dash 1. I get this equal to 3 by 2. Now in this case one can find this method a bit difficult, but there are many questions in which question can be done using this method only. So we must do this types of questions by both the methods. In exam, depending on the question, we will decide which method has to be used to solve the question. Let's try one more question. The question is for function g from R to R, which is differentiable function. The functional relation for gx is equal to g of y multiplied by g of x minus y for all xy belongs to R. G dash 0 is equal to a and g dash 3 is equal to b. Then find the value of g dash minus 3. Okay, how we start the question? We have given relation g of x is equal to g of y multiplied by g of x minus y. Now let's differentiate this with respect to x keeping y as constant. So I get g dash x is equal to g of y multiplied by g dash of x minus y. The derivative of x minus y is 1. Okay. Now I have here some derivative terms and g of y also. So let's put here x is equal to y. So I get g dash x is equal to g of x multiplied by g dash 0. The value of g dash 0 is a. So I get g dash x upon gx, this is equal to a. Now look at this ratio g dash x upon gx from differentiation point of view. How you see this ratio? We have derivative of function in numerator and in denominator we have function. Okay, what is that function whose derivative is this g dash x upon gx? Obviously this is derivative of log gx. So I can write this equation as log of gx derivative, this is equal to a. Now I can get log gx by integrating this. So I get log of gx is equal to ax plus some constant c of integration. We know some basic integration. The integration of a is ax plus c, where c is constant of integration. And certainly if we have derivative term and you integrate it, we get the function whose derivative is given. From this, okay, here the base of logarithm is e. Okay, so from this I get gx is equal to e power ax plus c. Actually we got the function this time. Okay, now how I get the value of c? To get the value of c, I must have the value of function g at some point, and the simplest point is 0. And for g of 0, I will use this again functional equation. In this I will put y is equal to 0. So I get g of x is equal to g of 0 multiplied by g of x. From this I get the value of g0 is equal to 1. So now in this put x is equal to 0. So I get g of 0 is equal to e power c, and g of 0 is equal to 1. This implies c is equal to 0. So my function is finally g of x is equal to e power ax. Now I can get the value of g dash minus 3. Okay, but I have also the value of g dash 3. Okay, so first of all let's differentiate this. G dash x is equal to a multiplied by e power ax. In this if I put x is equal to minus 3, so I get g dash minus 3 is equal to a multiplied by e power minus 3. Now what is the use of this value? G dash 3 is equal to b. Now in this I will put x is equal to 3. So I get g dash 3 is equal to a multiplied by e power 3a, and g dash 3 is equal to b. So the value of e power 3a is equal to b upon a. If I put this value here, I get a multiplied by a upon b. So answer is a square upon b. I am getting here g dash minus 3 in terms of a and b. So here we are using direct differentiation, but here there is something new. Here we are clubbing these two terms, okay, and this is derivative of log of gx. Then we are integrating this, we are getting function gx, and then we are finding the value of g dash minus 3. Okay, look at this question. F of x plus f of y is equal to f of x plus y upon 1 minus xy for all xy belongs to R and xy not equal to 1. Certainly here xy can't be 1. Also limit x tends to 0 of fx upon x is equal to 2. Find function fx. Now this is a known functional equation. Okay, any guess for the function? Which function will satisfy this relation? This expression is a known expression. We have tan inverse of x plus tan inverse of y is equal to tan inverse of x plus y upon 1 minus xy. So we can assume that the function is fx is equal to tan inverse x. But if I put this function in this limit, I have limit x tends to 0 tan inverse x upon x is equal to 2. This is wrong because this limit is actually 1. So I do some modification here. I will have here 2. So if I put now fx is equal to 2 tan inverse x, this limit will be 2. So this is one way, by observation we are finding a function. But if suppose we want to find the function using definition, first definition of derivative, then how can we find that? So let's start with first definition of derivative. First of all, we will find f dash x. Once we have f dash x, we will integrate it and find fx. Okay, the definition of this is limit h tends to 0 f of x plus h minus fx upon h. Now in this we will use this functional equation. The problem is here we have x plus h and here we have x plus y upon 1 minus xy. So it is difficult to use this relation in this direction. Okay. Also, if I want to use the relation in this direction, I have here fx plus fy, but here we have minus sign in between. So now to create a plus sign here, what I will do, in this I will put y is equal to minus x. So by putting y is equal to minus x, I get fx plus f of minus x is equal to f of 0. Now what is the value of f of 0? Again for this ask the mother equation. In this put x is equal to y is equal to 0. So I get f of 0 plus f of 0 is equal to f of 0. F of 0 gets cancelled out. The value of f of 0 is equal to 0. So here we have f of x plus f of minus x is equal to 0. From this the value of minus fx is equal to f of minus x. Let's put this value here. We have limit h tends to 0 f of x plus h plus f of minus x upon h. Now we can use this relation. In place of x we have here x plus h. In place of y here we have minus x. So this is equal to limit h tends to 0 of f of x plus h minus x upon 1 plus x multiplied by x plus h upon h. Okay, now we have this limit. What is next? Now we have this limit given, limit x tends to 0 of fx upon x is equal to 2. Now here x gets cancelled out, so I have h in numerator, and when h tends to 0, this expression, this entire expression tends to 0. So we can assume that in place of x, here we have this expression which tends to 0 when h tends to 0. So to use this, I must have same expression which is here must be here. Now this is h upon 1 plus x into x plus h. To create the same expression, I will divide denominator by 1 plus x multiplied by x plus h. So I will multiply here in denominator by the same expression. Okay, now this limit is equal to 2. The only change is in place of x we have this expression, and the limit of this, when I put here h tends to 0, I will get 1 plus x square. So I am getting this is equal to 2 upon 1 plus x square. This is my f dash x. Now f dash x is equal to this, that means function fx is equal to 2 tan inverse x plus c. We know the derivative of tan inverse x, which is 1 upon 1 plus x square. So for this derivative, the function must be 2 tan inverse x. How we find the value of c? For that I will put x is equal to 0. So f of 0 is equal to 0 plus c. The value of f of 0 is 0. That means c is equal to 0. So finally I am getting function fx as 2 tan inverse x. So again in this question we are using the first definition of derivative, from which we are getting actually the value of f dash x, and then we get the function fx by integrating. In that we may require the value of constant of integration. For that we will have a value of function at some point, and which we can get from given relation. Okay, now look at this question. We have function from R to R satisfying the functional equation f of x plus y is equal to fx plus fy plus x square y plus xy square for all xy belongs to R. Now if this limit x tends to 0 of fx upon x is equal to 1, we have to find function fx. So again we will start with first definition of derivative. Okay, so we have f dash x, this is equal to limit h tends to 0 of f of x plus h minus fx upon h. I think this question is simple because here we have f of x plus y. We can straight away use this here for f of x plus h. So let's use this. The only change is we have h in place of y. So this is f of x plus f of h plus x square h plus x h square minus fx divided by h. Okay, now fx gets cancelled out, so we have limit h tends to 0 of f of h upon h plus x square h upon h is x square and x h square upon h. This is x h. Now when h tends to 0, this value is 0, and when h tends to 0, fh upon h, this value is 1 because this limit is given. So we have actually 1 plus x square. So we are getting here f dash x as 1 plus x square. Now we can get the function by integrating this, and we have this simple integration of 1 plus x square. What is integration of RHS? We have x plus x cube upon 3 plus c. Here c is constant of integration. Don't forget to put constant of integration, though many times we get 0, but you must put c here. You may get c non-zero sometimes. Okay. Now to get the value of c, I must have the value of function fx at some point, and the simple point is x is equal to 0, which we can get by this mother equation. In this we put x is equal to y is equal to 0, so we get f of 0 plus 0 is equal to f of 0 plus f of 0 plus 0 plus 0. F of 0 gets cancelled out, so we get f of 0 is equal to 0. Putting x is equal to 0, now in this function we have f of 0 is equal to 0 plus 0 plus c, but f of 0 is 0, so c is 0. So finally function is fx is equal to x plus x cube upon 3. So we can see now we have many equations of this type in which functional equation is given. We use, in fact we start the question with first definition of derivative, from which we get derivative of the function, okay, and then by integrating we get the function. Okay, now see this question. F of x plus y upon 2 is equal to f of x plus f of y upon 2 for all x y belongs to R. F dash 0 is equal to minus 1, f of 0 is equal to 1, and we have to find function fx. Okay, so let's start with first definition of derivative. We have f dash x is equal to limit h tends to 0 of f of x plus h minus fx upon h. Now how can I use this relation? I have here x plus y upon 2, and here I have x plus h. So what modification I must do here? Okay, here I will multiply and divide by 2. So I have limit h tends to 0 of f of 2x plus 2h upon 2 minus fx upon h. Okay, now I can use this relation. Using this I get f of 2x plus f of 2h upon 2 minus fx upon h. Okay, let's simplify this. In fact, take 2 in denominator. So we have f of 2x plus f of 2h minus 2fx upon 2h. Okay, now we are given the value of f dash 0, which is minus 1, and here we have f of 2h, and in denominator we have 2h. So keeping this value in mind, I can write this as limit h tends to 0 of f of 2h minus, in the bracket I have 2fx minus f of 2x upon 2h. Now what's the reason I have clubbed these two terms? Here f of 2h and here we have 2h. That means I can make this limit definition of f dash 0. For that, this value must be f of 0. And we can confirm this from this given relation. Okay, what should be the replacements in this equation so that I get this is equal to f of 0. Okay, let's put y is equal to 0. So I get f of x upon 2 is equal to fx plus f of 0 upon 2. From this I get f of 0 is equal to 2 times f of x by 2 minus fx. Now here we have x and 2x, and here we have x by 2 and x. So simple, replace x by 2x in this. So I get f of 0 is equal to 2fx minus f of 2x. Okay, so let's put this is equal to f of 0. We get this equal to limit h tends to 0 f of 2h minus f of 0 upon 2h, and this is a definition of f dash 0. Okay, and the value of f dash 0 is given, which is minus 1. So I am getting now f dash x is equal to minus 1. F dash x is there, I can integrate, so I get fx is equal to minus x plus c, where c is constant of integration. Okay, and we can get the value of c by putting x is equal to 0, because we have here f of 0 is equal to 1. So f of 0 is equal to 0 plus c, so c is equal to 1. So function fx is equal to minus x plus 1. Okay, so this is first method in which we are using first definition of derivative. Let's find function fx by second method, in which we will be directly differentiating this functional equation. Okay, so now we have method 2. Using direct differentiation, I will differentiate this functional equation with respect to x, keeping y as constant. So I get f dash of x plus y upon 2 multiplied by half. The derivative of x plus y is 1. So I have here half. This is equal to f dash x upon 2, because derivative of f of y is 0, it is constant. Okay, now here the value of f dash 0 is given. So I will put here x is equal to 0. Okay, so I get f dash y by 2 is equal to, here 2 gets cancelled out, and f dash 0 is equal to minus 1. I can here replace y by x. So in fact y by 2x rather. So I get f dash x is equal to minus 1. So here I am getting f dash x minus 1 in just 2 or 3 steps. So in this question, this method is easier option. Okay. Now we will integrate this. So we get fx is equal to minus x plus c, and we already got the value of c, which is 1. So function fx is equal to minus x plus 1. So this is simple method for this question. But for this question I have one more method, which is graphical method. So let's try with alternative method, method number 3. And this method is very interesting. Using this we can solve, or we can prove many inequalities in trigonometry and calculus. Okay, now in this relation let's put x is equal to x1 and y is equal to x2. So we have f of x1 plus x2 upon 2 equal to f of x1 plus f of x2 upon 2. Okay, now let's draw graph of function y is equal to fx. Here we don't have function, so let's have general graph. You can draw any graph. Suppose this is a graph of function y is equal to fx. Now this relation is true for all x1, x2 belongs to R. Now what I am going to do, I will take 2 points on this graph whose abscissas are x1 and x2. So let's take one point, say this point is P. Suppose abscissa is x1, the coordinate will be f of x1, and here point Q, abscissa is x2, so ordinate is f of x2. Okay, let's draw perpendiculars on x-axis. Okay, now join these 2 points P and Q. Okay, why I'm doing this way? The reason is I have here f of x1 plus x2 by 2. Now can you tell me where I locate this abscissa? Certainly this abscissa will be for point which is midpoint of PQ. So let's consider midpoint R, whose abscissa is x1 plus x2 by 2, and the ordinate will be f of x1 plus f of x2 upon 2. Now tell me where you get this value f of x1 plus x2 by 2. Now this value is for abscissa x1 plus x2 by 2, and here we have abscissa for point R as x1 plus x2 by 2. So what I do, I draw one vertical line through point R. Now for any point on this vertical line, the abscissa will be x1 plus x2 by 2. Suppose this point is S. Coordinates of this point will be x1 plus x2 by 2, and ordinate will be f of x1 plus x2 by 2. So we have now two values, this and this, on graph of y is equal to fx, or on this figure. Okay, suppose this point is T. Now tell me which value is more, this or this. Obviously we have ST more than RT. Here height ST is this value and height RT, this is this value. So from the graph we have actually f of x1 plus x2 by 2, this is greater than f of x1 plus f of x2 by 2. But in the question we have these two values equal. Now suppose this graph is like this. The graph of y is equal to fx. If I draw this graph like this, in this case, here we will have less than sign. Now tell me, when we have equal to sign, obviously when this graph is straight line, because this is true for all x1 x2 belongs to R. That means now we have a graph a straight line, not concave upward or concave downward. This means this is possible only when function is linear. So we have linear function, and for linear function we have 1 point 0 comma 1, and f dash 0 is -1, that is a slope of the straight line. So we have function fx is equal to minus x plus 1. I am using the form of the line y is equal to mx plus c, where m is slope. Here slope is f dash 0, because on straight line slope remains constant at every point. Here m is -1 and c is y-intercept. Here f of 0 is 1, that is value of c. So this is a bit difficult, but this method is important in proving many inequalities. We will have separate section for inequalities in which we will be using this method. Now suppose in this question, if we have a relation f of say x plus 2y upon 3 is equal to f of x plus 2f of y upon 3, and all these values remain same. Again function will be same, because here we have taken midpoint, and for this relation we will consider a point which will divide PQ in the ratio 2 upon 1 starting from point P. In that case also the relation is satisfied by straight line only. So we can consider this is a shortcut for this types of relation. We can also see here this is a kind of section formula, isn't it? We have 1 into x plus 2 into y upon 1 plus 2. We have section formula for abscissa here, and here we have section formula for ordinate, and it is satisfied only by straight line. Okay, now let's try some questions in which a functional relation is given in the form of one inequality. Okay, here is the first question. The question is function f from R to R. Modulus of fx is less than or equal to x square for all x belongs to R. This is differentiable function at x is equal to 0. Then find the value of f dash 0. Now here we have inequality as a functional relation. In fact, we have functional inequality here. Okay, now we need f dash 0. The definition of f dash 0 is limit h tends to 0 of fh minus f of 0 upon h. Okay, now what is the value of f of 0? It is not given. We can find the value of f of 0 from this inequality. Okay, in this put x is equal to 0. So we get modulus of f of 0 less than or equal to 0. Now modulus of f of 0 can't be negative. So f of 0 is equal to 0. So actually we have now f dash 0 as limit h tends to 0 of f of h upon h. Okay, how can we get this? If we can get this, we get the value of f dash 0. Okay, again consider this mother inequality. Okay, mod fx less than or equal to x square. In this, if I put x is equal to h, I get modulus of f of h less than or equal to h square. In fact, I put here modulus. No problem, because we have h square which is non-negative, so putting mod h square won't change its nature. Okay. Now to have this ratio fh upon h, I will divide by modulus of h. So I get here modulus of fh upon h. This is less than or equal to modulus of h. In fact, I am creating fh upon h here from this given inequality. What's next? Apply limits. So we have limit h tends to 0 of modulus of fh upon h less than or equal to limit h tends to 0 of mod h. Okay, now we can take limit inside modulus. We have some rules of limits in which we can take limit inside modulus. So we have modulus of limit h tends to 0 of fh upon h less than or equal to 0. Okay, this is great because this is the value of f dash 0, and that too in modulus sign. So we have f dash 0 modulus less than or equal to 0. Again, modulus of f dash 0 can't be negative, so we have f dash 0 is equal to 0. Okay, now let's try one last question asked in IIT JEE exam. The question is if a function px is equal to a0 plus a1x plus a2x square up to an x power n. In fact, function px is a polynomial of degree n. If modulus of px is less than or equal to modulus of e power x minus 1 for all x greater than or equal to 0, then we have to prove that modulus of this value is less than or equal to 1. Okay, now how we start the question, what we should observe in this data. Can you relate this polynomial with this expression a1 plus 2a2 plus 3a3 up to n times an? Clearly, this is derivative of px at x is equal to 1. Okay, so that means we have to prove that modulus of p dash 1, this is less than or equal to 1. For any question, we must have some observation points. We must be able to observe the data. Okay, now we have p dash 1. What is definition of p dash 1? Definition is limit h tends to 0 of p of 1 plus h minus p of 1 upon h. For this, we will require the value of p of 1, and that again we can find from the given function or functional inequality. Okay, there's no point in putting x is equal to 1 here, otherwise we will get a p of 1 as a0 plus a1 up to an. Better we use this inequality. In this, if I put x is equal to 1, I get p of 1 modulus less than or equal to e power 0 minus 1. And now this is 1 minus 1 0, so modulus of p of 1 less than or equal to 0. Again, p of 1 modulus can't be 0, so p of 1 is equal to 0. So this value is now 0 here. Now I have limit h tends to 0 of p of 1 plus h upon h. Like in the previous question, we will try to create this ratio from this inequality. For that, it's simple. You first replace x by 1 plus h. So we get modulus of P of 1 plus h less than or equal to modulus of e power h minus 1. Next we have P of 1 plus h upon h. So in denominator I must have h, but I can't divide by h, because in inequality we have to take care of orientation of inequality while multiplying and dividing by some value. So to keep the same orientation of inequality, I will divide both sides by mod h. So I have P of 1 plus h upon h inside modulus. This is less than or equal to modulus of e power h minus 1 upon h. Now looking at this, when we see this, what strikes? Form of the limit x tends to 0 e power x minus 1 upon x. Okay. Next is limits. Apply limit on this, and we can take limit inside modulus sign. So we have modulus of limit h tends to 0 of P of 1 plus h upon h. This is less than or equal to limit h tends to 0 of e power h minus 1 upon h. Now this value is 1. This is one of the standard limits. So we have this equal to 1, and this is actually p dash 1. We have already here p dash 1 is equal to this limit. So we are getting modulus of p dash 1 less than or equal to 1, and p dash 1 is nothing but derivative of this function at x is equal to 1, which is this expression. So we have two questions from functional inequality. Again, in both of these questions we are using the first definition of derivative. So you can see that how powerful is the first definition of derivative. We have many questions in JEE Main and JEE Advanced from this category.